Welcome, everyone. We'll get back to this in a few slides. Starting out, as usual, with course announcements. So wanted to make clear that for problem 1 on the problem set, please don't just cite a result about n to the k being and don't cite a result about like polynomials necessarily and O of stuff and omega of stuff. It would be great to have like an explanation of why the definitions of big O and big omega hold here. Are there any questions about anything in the course? Or what I just said? It shouldn't be bad. I just want you to work through this. Yeah, 4 cute puppies are even better than 1. Okay. Let's move on. So before we get into the first of our graph algorithms, wanted to just finish up with heaps and in particular priority queues. So recall from last time that a max heap, we're going to be thinking about max heaps mostly today, is a binary tree in which the key, there's a key, it's stored in every node, and it's greater than the value stored by both of its children. A min heap is just the same with min instead of max. So this is, again, an example of a heap. Every node has a value stored in it which is greater than the value stored in its 2 children nodes. This is an index on each node that allows us to sort of refer to each node in order in the tree. But this is not the value stored. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 are the indices. And then 16 is the key, and 14 is the key there. And again, we always assume that a heap is nicely arranged in this binary tree so that each row, which is just like the row in the tree, is full except possibly the last one. So the depth of the heap is going to be on the order of log n. N is the number of things in the heap. And we're also going to assume that the last row, is one of the assumptions of the heap, assuming the last row has all its nodes as far left as possible. And this is easy, just, you can easily like move all the things in a binary tree over to the left just by swapping left and right children at different levels of the tree. Are there any questions about heaps? Don't tell me that you have heaps of questions. Puns are not allowed. Okay, so a review of priority queues, which we defined last time. So again, a max priority queue is a data structure that allows you to perform a bunch of different operations. You can insert something into the data structure. You can get the maximum of the stuff in the data structure. You can take out the maximum, and you can increase anything within the data structure. And similarly, you can have a min priority queue, which is a data structure which allows you to insert, take the minimum, extract the minimum, and decrease a key. Are there questions about this? I realize the word key is a little bit confusing if you are used to like key value language. Here, the key is the thing that's being stored there, so it is the value. Okay. So priority queues are useful across a lot of situations. We'll see a situation very soon. And the thing which we didn't go into last time, but which is really cool, is that a max heap can be used to implement a max priority queue. And similarly, a min heap can be used to implement a min priority queue. So we're going to start out by seeing why this is true. So the operations, again, that we need for a max priority queue are insert, maximum, extract max, and increase key. So let's go through each of them in turn. Do we have all of these already, like nicely implemented already in a max heap? And if so, which ones? So we have maximum since it's the root. Because of the heap property, the top thing has to be the maximum. Do we actually have insert? So we didn't do the insert algorithm last time, at least. What we did remember last time, in order to build the heap, was we arranged everything, and then we corrected mistakes. We didn't actually do insert. We didn't add things to the heap one by one. We took the entire heap and then corrected errors in it until it was really a heap. OK. So there are ways to do these other operations, but we haven't actually seen any of them yet. So if you're feeling like some of these are intuitive, then maybe. So let's go through the others now. Let's now try to do extract max. Could we extract the max? What are some thoughts on how we might extract the max? Just take it out. This is a problem. So you could take it. You could take the max out. Here's a heap. If you took the max out, then you could sort of take the max of this, and then you could take the max of, we could just sort of fill in all of the holes here, and keep on taking the max iteratively. So if we took out the 16, we move the 14 up here. We take out the 14, we move the 8 up here. We take out the 8, we move the 4 up here. But then sort of we have this awkward hole somewhere. There's like this gap down at the bottom. We needed to have all the final leaves all over on the side, and there would be a weird gap here. So that would be kind of frustrating. We'd have to like shift around stuff, and there wouldn't be a guarantee that we actually could move something else over here. Like if we suppose that instead of a 4 here, it was a 1 here. I guess that would have maybe been a better example. If there'd been a 1 here and a 2 here, then we like move up. I don't know if it's easy to visualize, but we would have taken away the 16, moved the 14 up here, moved the 8 up here. And then we would have had to, if this is 2 and 1 here, we would have had to move the 2 up. And then we would have 2 being the parent of 1. And we wouldn't have another way to find another thing over here, because there's no other key which is smaller than 2. So we could never fill this gap. So we'd have to do something a bit more complicated. So this is sort of the motivation behind why we don't just take out the max itself and then fix all the issues. Instead, we're going to do the thing that a couple of people suggested, which is we're going to swap the max with the final node here. So the final node being just, in this case, it's 1, but it could have been anything. The node that is furthest along. So like if we could get rid of, we could just take out this node and it would still be a heap. And so what we're going to do is we're going to swap 16 and 1. And then we have problems, right? We have two problems. One is 16 is greater than 7. The other is 1 is greater than both its children, 14 and 10. But 16 greater than 7 doesn't matter because we're taking it out. We just cut it off. So here is 16, cut it off. But we don't want to have 1 up here. And so instead, we do our correction procedure. And remember, we had this sort of bubbling down correction procedure, or bubbling up, I guess. Moving the thing, moving the 1 up here all the way down until it fits the heap property. So imagine we have the 1 up here. Then we have to swap it with stuff. So we swap it with its biggest child. We swap it with the 14. So we end up with 14 here and 1 here. Now we have 1 here. We swap it with its biggest child. We get 8 here and 1 here. Swap it with its biggest child. We get 4 here and 1 here. So this is how we get from here to here. What we've done is we've moved the 16. We exchanged the 16 and the last element of the last row, which in this case is 1. And we have then corrected it. So why does this work? We know that when we do the swap, it's no longer a heap. But the important thing for when we could do this bubbling down thing before, it was the two subtrees below the thing we were correcting had to be both heaps. So for example, if we were correcting here, then this would have to be a heap and this would already have to be a heap. But if this was the first mistake, then we could move this down. That was how we created a heap last time. Remember, we did the last row, then we did the next to last row, and then we did this iteratively. And so now we're saying we have the entire heap. The entire heap works up until this top, the root node. And then we have a problem in the root node, but we can just correct it. And we move this root node down, and then we end up with this. Are there any questions about this? Some people call this operation of bubbling down max heapify, but there's also like I think there's a tradition where heapify means to make the heap. And so that's why I'm not using the word heapify. But there is a tradition where it is called, where this whole bubbling down procedure is called max heapify. Oops, sorry. Okay. So the number of swaps that we're going to have to do here is going to be the depth of the whole tree, which is just order of log n. So that is going to be the time that we need for this. Any questions? Just swapped the root and the last element of the heap, and then we've bubbled it down so that it actually is a heap again. Cool. So yeah, we have extract max in O of log n. Oh, how long does maximum take? Yeah, O of 1 time, constant time, because it's just the root. It's very easy to find the root. Okay, so now we can try increase key. We've done maximum and extract max. Let's do increase key. So this process is basically the reverse of what we did. It's not quite the same as the kind of issue that we had before. So instead of bubbling something down, in this case we have to bubble it up. So if we increase a key, we know it's never going to be a problem for the things below it because it's already greater. It was, if we increased 14 to 20, it would still be bigger than 8 and 7. And so we'd have to just make sure that it wasn't bigger than its parent, which is in this case is 16. So making 14 20, we'd have to correct an issue with its parent. Likewise, if we take this 4 and make it 15 suddenly, it's going to have an issue with its parent in this case. So we can swap it with the parent, and then just keep on swapping it with the parent as much as necessary. And in each case, we're increasing the parent. So we're never going to end up, we're increasing the value at nodes. So we're never going to end up with a problem. Now, why can't we potentially end up with an issue if we move the 14 here? Why couldn't the 14 have been greater than one of these? Because we're swapping the 14 and the 15, why couldn't 14 have led to a contradiction? You know, suppose 14 were, you could have had something smaller here. Any other thoughts? Why? So what we're doing, again, is we're increasing the value of something, and then we're correcting any issues. We swap it with the parent, if it's smaller than the parent, and then we swap that again, and we keep on doing this. Yeah, so I mean, just basically the issue, the reason for this is that before you did the increase, 14 had to have been greater than everything below it. And so if you swap something, if you swap 14 and you move it down to here, it has to be greater than everything because these things were already below it. Like 8 and 2 were already below 14. And so 14 already had to be greater than both 8 and 2. Does it make sense? How long does this take? Don't forget the big O. It takes big O of log n. Important to remember not to forget the constant because each of these moves itself does take a couple of steps. So it's not just a single step. So it's not like exactly log n. Also, when we're saying log n, we're not saying what base we're in. And typically, you know, the base that matters for something like this might be base 2. But log n is actually like, we're using it in this class to mean base e. And log base e of n and log base 2 of n just differ by a constant. So, but yeah. Hence the O of log n being important. Okay. So now finally, we can do insert. How can we use the previous operations to do insert? So we already now have several operations. We have max, getting the maximum. We have extracting the maximum, so taking the maximum out and then keeping it as a max heap. And then we also have the ability to increase a value in the heap. How can we insert something? Remember, we currently have no operations for inserting anything into the heap. We just have operations for taking something away or for changing values in the heap. But how can we use these to actually insert something? Like a single line derivation of how to do this. you can just insert something really, really small at the end of the heap, like negative infinity. You know it's smaller than everything in the heap, assuming it's a finite heap. So once you've inserted that something really small, you know it's not going to mess up the heap because it's definitely smaller than its parent. But now what you can do is you have a heap, so you can run IncreaseKey to make it whatever value we want. I mean, basically, it's just inserting it at the end and then bubbling it up. So what time does this take? Yep, it's still O of log n. Same time as IncreaseKey, which is the critical thing. Adding something to the end takes almost no time. It's constant time. So the time is just O of log n. And so putting it all together, we have a way to use max heap as a max priority queue. And each of the operations is going to run in O of log n time. And maximum is actually just O of 1 time. This is not necessarily the most efficient way to make a heap. We may talk about Fibonacci heaps later. But it is a very nice way to implement a heap in a priority queue. Sorry, it is not necessarily the most efficient way to make a priority queue, but it is a very nice way to do that. Other questions? Okay. So now we have this nice these nice additional operations on our heap. Oh, there's a question. We're restricting to only positive values, right? No, we won't. We just were assuming that there wasn't negative infinity in the heap. We were restricting to finite values. Putting infinity in things is like really, it's not a good idea. I mean, look, if you had infinity in your heap, all you need to do is define another thing, which is like even more infinity, and then do the same operation. It's not a problem. It's just like. So we can insert pretty much anything into a heap. We can insert anything. Well, as long as it's an order, we can insert. If it's a max heap, then you have to be. Then the heap property means that each node, the value there is greater than the values at its two children. If it's a min heap, it has to be less than. So there has to be some operation. So there has to be some way to compare the objects. Yeah, exactly. There has to be some way to compare the objects. More questions? Also, the way to compare the objects has to be like a well ordering. So like, don't worry if you don't, if that term doesn't mean things, but. Oh, what happens if two objects are equal? Well, you can just like say, I guess I should have said greater than or equal to. It doesn't matter which, you can have something be the parent of something which is the same size. Okay. So how can we use our new operations on a heap to come up with a sorting algorithm? Say we have a list of n things. I give you a list. You have to do something and give me back a sorted list. So what's your sorting algorithm? Yep, you can create a heap out of the things and then extract. You can either keep on extracting the max. You could say, okay, this is a max heap, keep on extracting the max. The first max is your maximum element. The next max is like the one below that, and so on. You get all the elements in order. You could also do this with a min heap, going from the min elements, but you have to build a min heap. So the making the list into a heap, remember that's time O of n. You can extract the maximum. So what's the overall time for the whole heap? Like getting this entire sorting algorithm. Yeah, order of n log n. This is the worst case time, since each extract max call takes time O of log n. Or if you did it with a min heap, then it's extract min. Okay, so what we have now is we have the summary of the running times for all the things we looked at. We looked at insertion sort, which had worst case running time n squared, and the average was also n squared. It's really not very good. Merge sort, which had a worst case running time of n log n and an average running time of also order of n log n. Heapsort, which is the worst case running time of, we didn't prove that it's theta of n log n, but if assuming that you're comparing things, I think it is just theta of n log n. And we didn't look at the average case running time, but this is just the worst case running time for Heapsort. And then quicksort, we had the worst case running time being theta of n squared, but the average, or the expected in this case, it's the expected running time because there's randomness in the algorithm. That's what expected means in this case, is theta of n log n. Ugh, a lot of sorting algorithms. In practice, this is not the only, worst case is not the only thing you need to be looking at. Like quicksort is actually really quick in practice. And the expected running time is n log n. Heapsort is also very quick in practice. Questions? There are particular reasons why people use different sorting algorithms. Okay. And does dash mean average of Heapsort is not defined? Oh, it just means we didn't look at it. it's a thing. I mean, I think it's also n log n. When computing the running time, will we view the limit theorem? The limit theorem. I'm confused. What that question? Could you rephrase the question? Any more questions? In the meantime. Okay. So a review of graphs. We can talk about weighted graphs and we can talk about directed graphs. So in a directed graph, ij is not the same as ji. So edges have these little arrows. And there are also numbers on these edges. But oh yeah, sorry. Also in a directed graph, you can have between any two vertices in the graph, you can have either an edge from I to j, or an edge from j to I, or you can have both of those. Like here, you have two edges going in different directions, or you can have neither. Weighted graphs have a weight on every edge. And in this particular case, I guess, sort of an example, the weights are different going both, sorry, the same going in both directions. They wouldn't have to be. If you have two edges which are ij and ji, they could have different weights potentially. Okay. So shortest paths. A path between two vertices, S and T, is a sequence of directed edges from S to T. So for example, this is a path from, I guess, literally S to T, there to here to here. So the length of the path is the sum of weights along the edges. So this path would have length 10, 7 plus 3. The shortest path, or a shortest path, because there might be several, is a path from S to T that has the minimal length. There might be several such paths, or if you're working with positive weights, there is at least one such path. So the shortest path from S to T here, let's see. So 7 plus 3 is equal to 10. If you tried another path, you could do 7 plus 1 plus 4. That's equal to more than 10, I guess 12. So that's not a shortest path. But there is another shortest path, which is 4 plus 1 plus 1 plus 4. So here it's shortest in the sense of weight. Now, if you had an undirected graph, you could also do this. And if you had an unweighted graph, you could also do this. In an unweighted graph, that just the way that people treat that is all the weights are equal to 1, which means that the length of a path is just the number of edges instead of the sum of the weights on the edges. So that's why it sort of matches up with what we were thinking about before, where in an unweighted graph, the shortest path between two vertices is just the minimum number of edges between them. Yeah. An unweighted graph is just this, it's just a weighted graph where all the weights are set to 1. In an undirected graph, edges just go both ways. So you don't care, you could equally well take this edge this way and this or this way. Questions? Okay. So Dijkstra's algorithm. So the problem here is, given a connected graph, and connected means, again, you can get from any vertex to any other vertex by following some edges. Given a connected graph G that's weighted and directed, with weights greater than or equal to 0, given some vertex, find the lengths of the shortest paths from S to all the other vertices. And the reason why you want shortest paths for things, I mean, everything from, maybe the example that you think of most is like Google Maps, where weights correspond to like traffic time or travel time. But there are a lot of other situations where shortest paths are really important, not just literally in routing physical things. So, is there any vertex that's easy to work out the length of the shortest path from S? There's a nice example of a situation where you might have shortest paths be useful, like drug discovery, if there are like different costs associated with different paths to getting from one chemical to another chemical. Yeah, nice example. Okay, so neighbors. Is it true that you can easily, like, the easiest thing for the neighbors, maybe not. So like, suppose I'm trying to get from S to, I'm trying to work out the distances to all its neighbors. Well, if I were to pick D, for example, Is the distance from S to D necessarily the length of the weight on the edge, SD? No, unfortunately. If this were 2, then you could get to D faster by taking 2 edges. You could take 3 and then 2. A vertex that has only one path to it. Yeah, if there were just like S and then like T were just right here, right? Like, and there were only one edge, then that would absolutely be the case. It's generally not the case to have something like that, but it would certainly be useful. So what can we have in general? Like, is there a vertex that's easy in general? The vertex itself, yes, that has distance 0 from itself. But I did write other vertices. Is there any one of the neighbors which is easier than the others? There's a suggestion of a vertex that has no in degree and no out degree, so an isolated vertex, but it is a connected graph, so there aren't any isolated vertices. The neighbor with the shortest edge. So the edge that has the lowest weight. So if you had neighbors here, here, and here, 3, 4, and 7. Okay, so 3, if we took 3, well, that actually is really good because we could imagine, sort of summing up the lengths. I'm going to sort of use lengths and weights synonymously here. So you sum up the lengths of all of these other edges, you're going to end up with something more than the shortcut, because this was the shortest edge coming out of S. You're going to have to take one of these edges coming out of S. So if this is the shortest, there isn't any way to get to B faster. So the vertex B that is closest to S has to have distance equal to the weight from S to B. So is there, now we've got this, is there another vertex that's easy-ish? Can we just take the second shortest distance? No, we can't just take the second shortest distance because, suppose there wasn't an A. Suppose the second shortest distance were like this one, 7. There could be a shortcut from B to D. But is there anything we can do? The longest path. Like the longest edge away from S, that doesn't work either. In this case, 7 is again the longest edge, and there might be a shortcut. But there's a suggestion of thinking about the shortest paths from B instead of from S. So you could imagine taking the shortest path from B itself. Okay. I realize this example doesn't quite do it justice, but shortest path from B, in this case it's essentially 3 going back to S, which is kind of frustrating. But suppose this edge didn't exist or S doesn't count. You could go to D. But unfortunately, this edge could actually have been shorter. There could have been a shorter path directly from S to D. Like if this had been 5. But we can sort of combine these two ideas. We could say, what is the shortest if we consider both paths going S directly there? And then what is the shortest considering paths that go via B? And that can end up working. So suppose that we take the vertex A that is the the arguments, the vertex for which there's the minimum of the minimum of the direct length to Q. So this is an argument, sorry, I guess over Q. I should have written argument over Q so this is the direct distance from S to a vertex Q. This is the distance if you go, I am very sorry, this should have been a B. So I made two mistakes here. This should be WSB plus WBQ. I'll correct that in the posted slides. But yeah, so this is the distance if you go directly to Q. This is the distance if you go via B to Q. And so now why does this work? Well, if you have such a vertex A, what is the shortest path to A from S? Well, it either goes through S, or it either goes directly from S to A, or it goes via B to A, or it goes via some other vertex to A. Okay, so if it goes through S to A, then the weight is going to be, then we've already included the distance to get from S to A. If we are going from S to B and then on some long path going to A, we know that the shortest way to get there would have been to go we know that we have to sorry, one moment, there's an alarm going off in my house. One moment more, I'm sorry. Sorry, adventures from giving lectures from home it was a false alarm, fortunately. Okay, so let's think about this again. So there are, again, three cases. We're trying to work out whether if we pick the vertex A here, there could be another shorter path to A. So could there be a shorter path to A than is given by this? We're considering both paths S to A and then paths S to B directly to A. Well, no, there couldn't, because a shorter path to A would have to either go to B and then to some other vertex. So it would have to go like SBD. But we know that that A was the min of this. And so SBD has to be greater than either SA or SBA, because A is the argmin of this. I'll be explaining this again in the next slide, if you're not getting it now. So again, two cases possible. Either there is a shorter path going via B and some other vertex, or there's another shorter path going via S directly to some other vertex and then circling around to A. So why could there not be some path via S and D, for example? Well, because we know that SD is bigger than SA. And it's also bigger than SB, so it's bigger than SA and than SA plus BA. Who's confused? For edges that don't exist, fantastic. Yes. So let me give the general algorithm, and well done for people saying they're confused. I should have just written that argument out way more. For edges that don't exist, are we saying the non-existent edge has infinite weight? Yes, good call. So let's look at this now. I think this is a better picture. So what we're gonna do is we're going to say, okay, we're gonna explore the vertices of the graph one by one, and we're going to say we're going to color something in black if we've already explored it, and then we're going to consider each of the neighbors of a thing as we explore it. So we start out by, and we're going to like gradually come up with estimates of the distances to all the vertices in the graph. So we're going to start out assuming that everything is distance infinity away from S, except for S itself, where we know it's zero distance away from itself. And so what we're going to do is we're going to go through the neighbors of S, right? We knew the thing that I think we got straight from the previous slide is that the neighbor of S, which is closest to S, is definitely, we know that is the correct distance. So if we take the minimum of all of these, we can say, okay, this is at distance 5. But now what we can say is we can also say we know this is at distance no more than 10, because there is a path of length 10 there. And so we're going to update our estimate. We're going to say instead of being infinity away, it's no more than 10 away. And this is no more than 5 away, but we know it's actually equal to 5. Okay. Now we're going to go to 5, because this is the new vertex that we explored. And when we explore a new vertex, we're always going to look at its neighbors. So now we're going to look at the neighbors of 5. We're going to say, okay, let's look at all of these things. We know that we can make a path via sorry, I shouldn't have called it 5. This vertex is called Y. Look at all the neighbors of Y. We know that we can make a path from S to Y to T. And in this case, S to Y to T is 5 plus 3, which is 8, which is less than 10. So we can update the 10 and say, okay, this is now an 8, because 8 is less than 10. So we know that the upper bound on how far away it is 8. We have an upper bound for each of these other vertices too. This is 5 plus 2. We know we can get here in 7. We might be able to get there shorter, but we know we can at least get there in 7. We know we can at least get here in 5 plus 9, which is 14. So we keep on doing this, and at every point we have upper bounds. Okay. Now, how do we work out from here which vertex to explore next? Well, we have a guess for every one of the vertices. And our guess is based on going either from S directly or from S to Y. Okay. Now, let's take a look at some other vertex. Which one of these vertices should we explore next? We have a vertex with a guess of 7, a vertex with a guess of 8, and a vertex with a guess of 14. Which one should we explore next? Why is Z shaded? Because it's the one that we're actually going to explore. Yeah, sorry about that. We can explore the smallest. This is what we did here too. We took sort of our provisional guesses, and we explored the smallest one. But we can do this again here. This is what I was trying to explain sort of badly on the previous slide. This is the argmin of the min of this thing. It's just basically saying we considered both paths going directly from S. In this case, there wasn't a path going directly from S, but paths going from S and paths going directly from S and paths going from S to Y to the thing. Okay. So now, why do we know that 7 is the shortest distance here? Why do we know that this actually is a distance 7? Because everything else is larger. How could we have gotten to Z faster? Could we have gotten to Z in any way? Like, there are many paths to Z. We could have, for example, gone this way to get to Z. Why does any other path to Z have to be larger than the paths than 7? We always took the min. So suppose there is a better path to Z. It either didn't go through Y, in which case we accounted for it from wherever it went. If it went through T, then it has to be at least 10. So it has to be at least one of these other values. Likewise, if it went from S to Y and then didn't go directly to Z, but went like off some other way, it again has to be at least one of these other values, because these distances are the minimum distances for going anywhere else. As soon as you step off the path SY, you've immediately gone at least distance 7. If you went from S to T, or if you went from S to Y to T, you've gone at least distance, you've gone actually at least distance 8. If you went via vertex X, the first time you step off SY, you've immediately already gone more than distance 7. And you can keep on doing this. You can say, okay, well, we now know that this is distance 7. Let's explore its neighbors. We can explore, in this case, there's only one neighbor. We could explore this thing, and it gives us the length 5 plus 2, so 7 is the distance here, plus 6. And that gives us distance 13 to get here. And 13 is less than 14, so we update this at 13. And now what we do is we say, okay, what's the minimum distance to get to any of these other vertices? And 8 is less than 13, so this is the one we need to go to next. And we know that this is distance 8 because there couldn't have been a shorter way to get here except via the vertices we've already explored. So next time, we can see a formal proof of this. But hopefully this should give you an intuition for why this is the case. Next time I can go through a formal proof and also show how to implement this.